down below the fusion temperatures, otherwise this whole endeavor will collapse. And the third and the biggest problem that arises is that if you are using a material in the walls of the tokamak that is, for instance, suppose lead, or any material which has the higher atomic number value, what happens is that that heavy nucleus would fall into the reaction chamber. This part where the plasma exists in the reaction chamber is known as the plasma minor. And if it goes into the plasma minor, it will be a part of a neutron-rich environment. And what happens in such environments is that, imagine that this is a heavy nucleus. What happens is, like these edge instabilities, some of the particles from the walls of the tokamak will go into the fusion reactor or the fusion chamber, plasma minor. And now this heavy nucleus will be in the path of those highly energetic electrons. When that electron will pass through the vicinity of that heavy nucleus, it will deflect, causing a scattering which will lead in the bremsstrahlung radiations. And if your Z is greater than 50, the atomic number of the particle which constituted of this particular nucleus, the X-rays that would be emitted from this part would be, the photon which will be emitted will be at the X-ray spectrum, which will not only cause the plasma cooling, but at the same time will harm the people who are working over there, hence jeopardizing the claims of fusion reactor as a clean energy source without any radiation problems. So, this is where ITER comes up with its ingenious ideas to develop the ITER blanket shield module. ITER blanket shield module is like, if you are to look at this floor is now covered with carpet. So just imagine that it has a lot of tiles on it, right? Now those tiles are comprising of the inner wall of ITER, each tile is the size of 1 by 1.5 meter. And if you are sitting inside of ITER, for instance, right now, you would have walls covering you all around, with the most fundamental unit being this tile, right? And this tile contains all the secrets of tokamak, which is keeping it stable, useful, and might actually help in commercialization of fusion energy. Now, the first wall is the most important because it faces the brunt of fusion environment. And the later sections, it actually has two walls. The first wall with 3 components, and then the later wall, it has some finger-like structures. I will go into that detail after it. And the later section uses that heat which is generated within the system to warm up the water, which is present within those walls. I will talk about that in the later slides as well, to generate electricity. And it also keeps the system from melting through cooling of those walls. So what happens over here is that, let's just take a look at the first wall. This first wall, it contains beryllium tiles. It's about 6 to 10 millimeters thick, and it is doped with lithium. And this is actually extremely important because the greatest fusion cross-section is that of a DT reaction, deuterium-tritium reaction. It is about 1,000 times more probable than any other fusion reaction. Deuterium is fairly ubiquitous, and as long as there is water in the oceans, you can always extract deuterium from the oceans. But tritium, it's only present in trace amounts, trace quantities, and it is really difficult to purchase tritium at a commercial scale. So what happens is that they use a beryllium tile on the surface, on the front, as a screening tile, which would be facing the brunt of the fusion environment. And this beryllium will serve a lot of purposes. First purpose, remember those bremsstrahlung radiations that I was talking about? Now, even if those plasma instabilities, what actually happens is that the bigger the curvature is, the bigger the circle is, the smaller number of particles will drift away, right? And so, since ITER is a huge machine, the concept of melting of the walls wouldn't be that big of a problem. But the concept of bremsstrahlung radiations and the cooling of plasma would be the bigger problem in case of ITER. In case of small fusion reactors, small tokamaks, the melting of walls would also have been a huge problem. But what they do over here is that this beryllium, imagine that there is a heavy particle which sputters some of the particles out of beryllium into the fusion environment. What will happen? Again, it would be present at this, imagine that this is its electron cloud, and beryllium is present in the center, and an electron from a highly energetic electron comes through it and then gets deflected. Since it has the atomic number of 4 only, what happens is that the energy of the power radiated through bremstalling only corresponds to infrared radiations. And it lies beyond the fundamental frequency of the plasma which is produced within the walls of the tokamak. And hence it gets reabsorbed and no heat is lost. And the plasma doesn't get cooled down. Better yet is that beryllium is a neutron multiplier. It not only absorbs neutrons, but also multiplies it by breaking down into a smaller nuclei and leaving a neutron. And what happens is that those neutrons, they create a neutron-rich environment in the presence of the like over here there are some lithium quantities doped, right? And those lithium would then be present in a neutron-rich environment. And when those neutrons, those low-energy neutrons, combine with the lithium nuclei, it would generate tritium. And that tritium will go into the system, and this sheet, it would not only prevent the plasma from cooling down and protecting the people from harmful X-ray radiations, but it will also act as the breeder of one of the most expensive ingredients of fusion. And it is truly genius and remarkable. However, there are some problems. If you were to use a beryllium sheet only, what happens is that it would get heated up too quickly, because it is not only at the face of the fusion environment and drifting particles, but also deterioration also produces a neutron, a high energy neutron that gets to this wall, because they cannot be deflected by the magnetic field line. They will always move tangent to the path that their parent atom was taking, because of course they are neutral in nature. So what happens is that, ma'am, can I take like 5 more minutes? Thank you. So what happens is that this beryllium, it can get heated up pretty quickly and it can melt. So what happens is that they add a copper zirconium nickel alloy beneath the beryllium layer, and it has some active coolants in it. What's active coolant? Active coolant is like when you use energy to cool something down. Like passive cooling would be like water is already present in there, and it'll get heated up, and then water will come back and the cool water will go over there, and it would be taking energy out of the system. Active cooling is that you're giving it some energy, like you're giving some pressure to the water to go towards that place and get heated up and keep the system cold. And of course you're giving it more energy than what you're receiving, but once those active coolants reach from this copper zirconium nickel alloy into the stainless steel chamber, what happens is that over there passive cooling takes place, and this kind of steel, 316L steel, is fairly flexible in nature. It's not like a very rigid steel that can get, it's not brittle. What happens is that in fusion, the walls, they can get expanded and contracted pretty quickly because of the fluctuations in temperature are like even like 0.001% fluctuation in temperature corresponds to hundreds of Kelvin temperature, right? So what happens is that it can easily expand and contract without breaking the walls of the tokamak. And some of the fluids, they wash through this place and go to the latter wall. The latter wall contains finger-like projections. In fact, I found a picture of that as well. Let me just show it to you. Yes.
Just a moment. इसको बंद करो, दोबारा start